Okay, so you're able to see my PowerPoint slide, yeah?
Yes.
Yeah, okay, so previously we stopped at the fully developed laminar flow in a pipe. So we have developed some previously we discussed about plate, two plate, and then now we look at a pipe. So a pipe, there's an equation for the velocity profile. So we have covered all this equation, and then we stop at one of the slides here. So we stop at these three velocity profile. All right. So if you want to calculate the velocity u in a pipe, so you are free to use either these three, depending on the type of the question you have. Sometimes it's more easier to, normally you will see the second type question and the third type question. So it depends on the question that you have. If you are given the r, the radius and the distance from the center, then you use a second one. And normally, if you have the ratio between the r and r, then you are free to use the third one. So the second one and third one is quite popular compared to the first one. Okay, first one you can still use, but the second one and third one is more simpler, right? In mathematics steps. All right. So last lecture we stopped at these three equation about the velocity vector, velocity profile for pipe. So when we have the velocity, we able to develop equation in terms of shear stress. So again, this equation is for Newtonian fluid. So shear stress Rs in this time, there is the notation that we have for shear stress is a little bit different. Previously, when you talk about plate, then you have yx, but you talk about pipe, then you use radius, r in the radial coordinate. So you use the rx equal to mu du dr. So previously you'll see this one as your y, du dy or du dx. So in the pipe, you use radius as our reference. Then you rewrite the equation, shear stress Rx equal to R divided by 2, the pressure differential, the pressure difference along the x-axis. All right. Then you can use this equation to calculate the volume flow rate. So volume flow rate Q equal to velocity times the cross-section area. So Q equal to VA. Then because if you are using the dA, integrate area is a bit difficult to calculate. Normally we'll use the radius, the distance from the center, 0 to r. R means the outer radius. Capital R means the outer radius. So from center to outer radius, and then we change the area to 2 pi r times the dr. So we get the area. Okay, dA we change to 2 pi r dr, integrate from 0 to outer radius r. So the velocity vector is a u. So u here is the three equation that you see on the screen here. Right, either these three works for this equation. So these three velocity profile, if you take this one times the area, you're able to find the volume flow rate. All right, so the rest is just a mathematics substitution where you look at the slides and then you substitute the u equation inside the integration equation here. Then you do integration. At the end, you arrive at the equation at the bottom of the screen here. Q equal to pi r. This is a capital R, which refer to the outer radius. R power 4 divided by 8 mu. This mu is the dynamic viscosity. Don't confuse with the kinematic and dynamic. So this is a dynamic viscosity that you use to calculate the Reynolds number, and the graph in the appendix A. And then you times the dp over dx. So this one you calculate from the mathematics model. All right. So far, any question about how to find the Q, the volume flow rate?
No, sir.
Right. Good. All right, then the next one, we want to put our volume flow rate in terms of pressure drop, which is a delta P, because this is a pressure differential. We want to put in the delta P, means that we can take the difference pressure between 2 points directly. So how do we write mathematically? So these are all the mathematics derivation. Important is you can directly change the equation on the left hand side into the right hand side. So previously is in terms of dP over ds is the differential pressure differential, and you can, when you write in the function of pressure drop, you can change it to minus delta P over L. Minus delta P over L. Why there's a minus there? Because normally, because dP, you take 0.2 minus 0.1. So normally 0.2, the pressure will be a bit low compared to 0.1. So you take a small number minus a big number, you get a negative sign. Clear, Amir?
Yes.
Right. So there are two format about volume flow rate. One is the Q in terms of dP over ds, partial differential, or differential pressure differential. Or another term is in terms of pressure drop, which is a negative delta P divided by L. Then you rewrite the equation, you rearrange the equation, you will get, because previously you get a minus minus, so if you write in the pressure differential, the PDS, there's a negative sign in front there. But if you write in the pressure drop term, the whole equation become a positive sign, because negative in this equation, you get a positive sign. So pi delta PR power 4 divided by 8 mu L. Okay, so this is the differences between volume flow rate. There are two formats. One is in terms of negative with the dP dx. Another one is the positive with the delta P in the equation. So be careful when you want to use which one, right? If you use this one, you need to know that there's a negative sign. If you want to use this one, there's a positive sign for the answer. Another one, if you sometimes the question will give, most of the question will give you in terms of diameter, or in the industry later on, if you after you graduate, you work in industry, most of the time in the spec table, specification table, they will be given the pipe, they will be given in terms of diameter rather than radius. So you just change the R equal to D divided by 2 and then power 4, you will get pi delta P D power 4 divided by 128 mu L. Okay, any question on the conversion from 8 mu L to 128? You understand why certainly become 8 to 128? Okay.
So, sir,
yeah.
The only difference that happens here in the volume flow rate, so only the place that I want to use it, right?
Yeah. The left hand side means this quadrant, this left hand side equation is when you have the partial differential dP over ds equation given.
Okay.
Yeah. So if you have a equation P equal to something x plus something, means your pressure is in terms of equation. Then you can do differential. You do differential, then you use the left hand side equation. You understand?
Okay.
So for example, just to a side note for the other two member. So if your pressure is in term of, let's say your pressure in the question give you like for example 8 x power 3 plus 4x, something like that lah. Your pressure is in term of this equation. So you cannot use this equation directly from here, because the right hand side is this pressure drop, different pressure. So how you calculate the volume flow rate is that you differentiate the P over dx. So in this case, let's say we have 8x power 3 plus 4x. So you will get 24x power 2 plus 4. Then you you will substitute this one, the whole thing inside here.
Okay.
Right? Yeah, so you have X value there. So it will depends on the location of the X in the pipe. So in the pipe, your X location here. So if you have given the location, then you might be careful on the X location. So X1, X2. So X1 will give you a 1Q value there. X2 will give you Q2 there. So yeah. So yeah, I mean the concept, how you apply the equation is that if you are given a pressure in terms of equation, then when you can differentiate it, then you use the left-hand side equation. So if you directly you have let's say two places, P1 and P2 value is given, then you straight away use the left-hand side equation.
Okay.
Yeah. That is the only difference. All right. Both will give you same answer actually.
No.
Yeah. So this equation, just take note, this equation is for laminar flow only. This equation is only work for laminar flow.
Okay.
So again, when you see the word laminar, means that you need to recall back the Reynolds magic number, right? The 2300. So the number must lower than 2300. Then this equation can be used. So normally when it comes to exam, there will be one particular section to ask you to explain what is the type of flow for in that particular plate or in that particular pipe. So you need to, from there you use Reynolds number, you determine the Reynolds number whether it's laminar or turbulent. Then you use the next step will be you use the respective equation to solve. Okay, so this we still at the laminar flow, right? Laminar flow. Okay, we move forward. So since just now we cover the two equations for volume flow rate, one is the partial differential pressure, and one is the pressure drop. We can write our equation in terms of average velocity magnitude. So sometimes the question give you average velocity, V hat. So how do you relate all this information to calculate for your Q? So we know that Q equal to VA. So we can write average velocity equal to Q divided by area. And area in a pipe is pi r square in a pipe. And you can substitute the first one, the equation first one, Q divided by, you take the first equation, divided by pi r square, you get this equation, minus r square divided by 8 mu dp dx, yeah, to get the average magnitude here. So later we will substitute this one in our equation. So just remember that we have this equation, average velocity equal to minus r square divided by 8 mu, and the pressure differential at this location. Then from here in a pipe, you can find the maximum velocity. So to find the maximum velocity, du over dr means that we differentiate the velocity profile at the right hand side here. Equals 0, we'll get the maximum velocity profile or maximum value there. So when this is the boundary condition to get the maximum velocity, call it boundary condition. So if you're using software to do analysis, then this is one of it. We call it boundary condition. So boundary condition is that at the middle of the pipe, at the middle of the pipe where this is your R axis, this is your X axis. So we know that in the middle of the pipe, there's no friction in the middle. So we always get the maximum velocity in the middle of the pipe or middle in the plate. So this is the first boundary condition that we use. Du dr equals 0, because we know that we have a parabolic shape. So we want to get the point at the peak there. So du dr equals 0, which is here. At r equals 0, we can get the value there. So if you differentiate and you substitute the equation on the right hand side here. So you du dr, you can differentiate r either one, right? Either one. And then after that, you put du dr equals 0. Substitute all the r term in the differentiate equation equals 0. Then you rearrange the equation. You'll get u equal to u max equal. You'll get your u equal to minus r squared divided by 4 mu dp dx. So after you differentiate this one with the r, and then you substitute all the r with equal to 0, you will get this term. You will get minus r squared 4 mu dp over dx equal to u. All right, equal to u. So your u max equal to this one. This equation, you see the yellow color that I highlight. So this one actually you want to link up with the average velocity just now. So average velocity equal to this one, equal to minus r squared 8 mu dp dx. And then the maximum velocity equal to this term. So we substitute or we transform this equation in terms of average velocity. So your u or your u max will be equal to 2 average velocity in the pipe when you have a laminar flow. Okay, yeah. So sometimes the question, after you find the velocity in the pipe, then the next section in the question will normally ask you, what is the maximum velocity in the pipe? And then when you calculate the Reynolds number, you found that the flow is laminar. So straight away you can use this equation on the left hand side. You can write du over dr equals 0. At r equals 0, then you calculate u max equal to u equal to minus r squared divided by 4 mu dp dx. And then you recall the average velocity equal to minus r squared divided by 8 mu dp dx. You substitute in the equation, you write u max equal to 2 average velocity. So from there, you can either find average velocity or the maximum velocity. It depends on which one information is given. Okay, any question on this side, on this page?
No, sir.
Right, quite clear, huh?
Yes.
All right, so let's check the attendance. Okay, Koo and Oliver still not here. All right. So once we find the 2v hat, the average velocity, so we can write in terms of the ratio between u and u max. All right, if you rewrite this equation, you rewrite the velocity profile, you can write u divided by capital U will be equal, capital U is at the center velocity, yeah? Capital U is the velocity at the center, and we know that velocity at the center for laminar flow is maximum. So we can use the capital U to represent the maximum velocity, or equal to 1 minus r divided by r squared. Okay, clear? Huh?
Yes.
All right. So in this ratio, you can find that this is actually a parabolic profile. If you plot your y versus your y is r versus your x is u divided by u, or you can plot your y equal to u divided by u versus your x. Your x is 1 minus r divided by r. So you can plot this graph. This one is this term is for y-axis, this for x-axis, then you'll get a parabolic behavior. All right. So this equation is used for this section when you have a fully developed velocity profile. Okay, so this profile is represented by u divided by u equation. All right. So any questions so far for all these slides?
Yes.
Okay,
Yeah.
good, eh?
Yeah.
All right, so let's look at one example. All right. So let's look at one example. All right, so this slide is inside your hands out also inside your tutorial question. So we have a simple and accurate viscose meter that you have see in our screen here. So it's made of the length of a capillary tubing. So it's a very small distance, the diameter, because we have a capillary tubing. The word capillary means it is a small space there. If the flow rate and pressure drop is measured and the tube geometry is shown as in the diagram here, the viscosity of Newtonian liquid can be calculated using this equation. Q equal to pi delta PR power 4 divided by 8 mu L, or another one is divided by 128 mu L. So this one we already covered just now in class. All right. So a test of the certain liquid in a capillary viscosity is given the following data. So you are given the flow rate so and so, the tube diameter is so and so, length is 1 meter, pressure drop is 1 megapascal, right? Pascal is Newton over meter square. We need to determine the viscosity of the liquid by using this equation. So if you look at this diagram, you have a capillary tubing. You have a two end there, 0.1 and 0.2. The different length, or the length between 0.1 and 0.2 is 1 meter. Flow is flow from the left to right. Diameter is very small, 0.5 mm. All right, and this is our control volume with a dashed line there. Pressure differences, delta P is 1 megapascal. So this is delta P equal to P1 minus P2. So we take the differences between the two magnitudes. P1 minus P2 is 1 megapascal. So we take all this information and then we take this equation to calculate the viscosity. Right. So the rest is just a mathematical substitution. Important is that when you analyze and we use this Q equal to pi delta P R power 4 8 mu L. Remember that this equation is for laminar flow. This equation only works for laminar flow. And then steady flow, incompressible, fully developed, and we have a horizontal tube, meaning there's no angle, there's no differences in the horizon. You rewrite the Q equation in terms of viscosity mu, and this one is our dynamic viscosity, mu equal to pi delta P d power 4 divided by 128 LQ. You rewrite this equation in terms of viscosity. Then the rest is just substitution. Only need to remind is to convert all the diameter, all the dimension into unit SI. So it means that mm into meter. The Q, the flow rate is given in mm cube per second. The flow rate, be careful, it is in mm per second. So in exam, you will see a similar format also. You will see mm cube. So you remember to change this one to meter cube. All right. So the rest of the slide is just a substitution of the value. So the textbook answer or the checkpoint answer for you, if you substitute all the numbers into the equation, you'll get 1.7 10 power negative 3. The unit for viscosity is Newton second over meter square, the dynamic viscosity. So in exam, you're not sure what is this unit, you just can go and refer to Appendix A. There's a table for dynamic viscosity. So go ahead and refer to that table and then write the unit there. Okay. So the next step is that normally the question will add on to say that prove that the flow is laminar or turbulent. So you use the Reynolds number to prove whether it is a Reynolds number, whether it's laminar or turbulent. So if you use this number, Reynolds number equal to rho Vd divided by mu. So you have a average velocity there. So rho average velocity times the diameter of the pipe divided by viscosity. So you will find if you substitute all the numbers there, all right, you will get the number around 1290. So this number is less than 2300. We prove that the flow is laminar flow. All right. So in this question, the average velocity is not given, right? The average velocity is not given, but however, from Q itself, you're able to find the average velocity, right? Q equal to VA, right? So from there, you find the average velocity, and then you can calculate the Reynolds number. Any question for this tutorial question?
No, sir.
Right, you're good, eh?
Yeah.
All right. Okay, so the next one we look at shear stress. So we already done for the pressure differences. We already done for the velocity Q there. All right. Okay, we will go a bit deeper, and then we call it a day. All right, so now we look at shear stress in the fully developed pipe again, shear stress distribution. So we need to determine what factor that that affect the pressure inside the pipe, right? And we assume that our fluid is incompressible. So the first thing you look at is the Q. The Q equation equal to pi delta PR power 4 divided by 8 mu L. So you can write in terms of diameter. So you rewrite the Q equation where you put the pressure drop delta P equal to this term 128 mu L Q divided by pi D power 4. And from there, you can calculate the pressure. All right, so this is the equation that we previously seen when we developed the equation. So the shear stress equation given you by this, R divided by 2 dP over dx plus C1 divided by R equal to shear Rx, right? So this one, if you forget already, refer to the previous PowerPoint slides. Yeah. So important is for today's lecture is that recall the shear stress is in this format. We need to remind ourselves that we cannot have a infinite stress at the center line. So means that at the center line of the pipe there, there's no friction. So when you have no friction, your stress is, you can say that there's no stress there. So when you do this calculation, your C1 will be 0, right? Your C1 will be 0. If you integrate the equation to get the C1, or you substitute the boundary condition, you will get your C1 will be 0. Then you recall the Newtonian fluid equation, the shear stress for Newtonian fluid, shear equal to mu du dr. You rewrite the equation again, so equal to R divided by 2 dP dx. This equation works for either laminar or turbulent flow. So again, to just take note, this equation that you see on the screen here, it works for laminar turbulent flow. All right. The rest you can read from the slide itself. Okay. So this is about the derivation for the shear, the stress at the wall were given you by the shear stress in terms of the boundary condition that you have, R equal to R. So this one, R equal to R means the shear stress at the wall, right? The shear stress at the wall where your R equal to capital R. You can substitute the R in the equation, this equation on the screen here with the capital R. Then you'll get a negative R divided by 2 dP over dx. And about the turbulent, the differences between turbulent and laminar flow is you look at the velocity vector there. So if you have a laminar flow, means it's very the flow is uniform in one direction. In this case, the flow is flowing from the left to right in x direction. So you write your velocity vector equal to ui hat. Then if you have a turbulent flow, means you have a three-dimensional vector, where sometimes you move to x, sometimes you move to y, sometimes you move to z, and so on. So you have the differences between these two. All right. Yeah. So the rest you can read from the screen here. So the total stress for turbulent flow is the combination between laminar and turbulent. So if you want to calculate the total stress for turbulent flow, you need to calculate the shear stress in laminar and shear stress when it is turbulent. Then you get the total stress for the pipe or for the duct system. Okay. However, the turbulent flow is quite complex, so most of the time for this module, we will only focus on laminar. Okay, so this is just add-on information. When you're being asked by expert or you asked by other lecturer, ask you, do you understand the differences between laminar or turbulent, right? How you calculate the total stress for when you have a turbulent flow. Means that you take the laminar flow shear stress times the turbulent shear stress, then you get the total stress for the turbulent flow scenario. Okay, and this is the information, right? You don't need to memorize. All these are available in the PowerPoint slide, so at least you've seen this equation before. So if you read textbook, you will see these two equations. So what does it mean by the second term? This is your Reynolds stress. Rho u v hat is all these are u hat, v hat is the velocity component that you have in the turbulent flow. All right. So if you take the velocity, take the density times the u hat, v hat, or u prime, v prime, and the average of them, then you'll get a Reynolds stress. And if you plot the turbulent stress, the stress in the turbulent system, you can plot y is, the y-axis is negative rho u hat, v hat, or u prime, y prime divided by your shear w, the wall stress, and versus the dimensionless distance from the wall, where you take y versus r, y divided by r. So you can plot the Reynolds number. So this is the one of the experimental data from Lofer, where this researcher, he did for Reynolds number 500,000 and 50,000. So you see that both give you the turbulent condition, and you see that the relationship between these two cases in the experiment is quite near, right? Both of them give you almost a linear equation between the two parameters that you plot in the y and x axis. Okay. All right, so this is about turbulent flow in a pipe. If you recall the equation that we looked at just now, the shear stress in the system, in the turbulent system, you combine laminar and turbulent, where you get this equation, and then you divide the equation with the density. So the right hand side, the left hand side, you will have shear divided by density, and this one, the dynamic viscosity. If you dynamic viscosity divided by rho, it will become kinematic viscosity. Yeah. So be careful. This one will change to kinematic viscosity, and if you have a fluctuating velocity is given by this equation, fluctuating velocity u prime equal to this equation minus L, the differences of velocity in terms of y, and then another one is your v prime or V prime is a vertical fluctuation, V component velocity given you by this equation. You put these two together, you will, and in our derivation, we go for a homogeneous turbulent condition. So these two will be the same. You can write your U prime V prime equal to one equation, L divided by U divided by dy. So your turbulent shear stress, there is an equation for that. So you can always refer to these slides when you want to find the turbulent shear stress. You take the shear turbulence divided by density equal to length, mixing length, the length that mix between laminar and turbulent, the length square divided by du over dy. So again, du over dy, this one, you take the velocity profile, you differentiate with y. With y, then you power square, you get the turbulent shear stress in terms of divided per density. Then you can plot the graph. So why I'm showing you this graph you're seeing that on the axis that you see here is not a common one. It's not a common one, but it's a very important when you study about fluid mechanics or fluid dynamics, or even when you want to use a flow simulation, right? In the future, maybe you want to look at if you use ANSYS or if you use any simulation software to simulate flow, then you will see these two parameters, the U plus vector, not vector, U plus parameter on the y-axis and y plus on the x-axis here. So you will see these two parameters in the simulation software, U plus and y plus. Right. So this graph gives you the mean velocity profile for fully developed turbulent flow in a pipe. Okay, it will defined by the U plus and y plus constraint. Right, U plus and y plus, and as you can see from the graph here, you have a two laminar flow there. Not laminar, two Reynolds number here. Reynolds number 10 power 5. Reynolds number 5 times 10 power 5 is over here, and then you have a region where your U plus equal to y plus. So what does this U plus and y plus basically mean? It means that it is a wall coordinate. Just take note. So when you use software or when you use a simulation software in the future, you need to key in or you need to plot the wall coordinate to differentiate or to find that particular temperature or pressure or velocity at that particular wall section. Then most of the time we will use wall coordinate U plus and y plus. Right, so this U plus y plus normally is only spoken by expert. Means U plus y plus is not a common language when you communicate with common people in the public, but you will see U plus y plus when you communicate with flow simulation expert or any researcher that are doing research in the flow dynamics or flow mechanics. Right, so it's a parameter used to define the characteristic of the flow. So it's given by these two equations, right? So we won't go deep into the derivation of these two, but at this moment, what is important is that you know what is U plus, what is y plus. U plus, y plus is a wall coordinate. So U plus given by U divided by U star, y plus given by yu star divided by mu, divided by this mu. So the U star is a friction velocity. Right, U star is a friction velocity given by this equation, square root of the shear at the wall, the shear stress at the wall, divided by your density. And just now, recall that we have an equation for our shear turbulent divided by density equal to L square divided by du over dy square, right? Don't worry about all these equations. Just try to follow along. And then you at least in today's lecture, you heard before what is wall coordinate. And then in this lecture, you know that there's an equation for u plus, y plus, and then you know what is friction velocity, how we define friction velocity. Friction velocity, we take a square root of your wall stress, wall shear stress divided by density. Then you put into this equation. So there's a note there, there's a note there. So for the flow away from the wall, but still near enough to the wall, the total shear stress will equal to the wall value, the shear wall value. The laminar stress is much smaller than the turbulent stress. So you can write your equation in this term. Yeah. Again, don't worry about the format of the equation. What is important for today's lecture is that you know that there is an equation to calculate turbulent shear stress, right? So this is the equation to calculate the turbulent shear stress. K square y square and du over dy square. Then you write in terms of your wall coordinates, u plus, y plus. And then you square root both sides of this equation. You will get 1 equal to k y plus divided by u plus divided by y plus. Right? So all these are new equation, I believe so far, for from your year 1 module. This is a new introduction about fluid mechanics. So this is a little bit deeper, but don't worry, it won't come out in the exam. It just give you some exposure to turbulent velocity profile, right? Then you have an equation between the y plus and u plus. So u plus equal to 1 over k. K is a constant value that you determine from experiment. Ln y plus plus c, because if you continue with this equation, you integrate with y, right? You will get this equation. So you will get the, you can only determine this y plus, u plus through experiment. So from a common experiment, the k is a common constant, is given 0.4. Constant c in the experiment is 5. So you can substitute the value there. So this is just an example. Because each experiment will give you different u plus, y plus. So this k and c you need to determine from experiment. Yeah. So this is just an example where your k is 0.4, c is 5. Then you can plot the graph between u plus and y plus. All right. This is just a recall what is the equation for u plus and y plus. All right. So from here you can plot the graph between your y-axis and x-axis. All right. So this is the turbulent equation. All right, just a summarize of these slides, or what is about turbulent condition. A turbulent velocity profile in a fully developed pipe flow is that the one that I highlight with the box on the screen here. All right. When you see u plus, y plus, normally we talk about turbulent flow. Yeah? And there's an equation for that. Yeah? So if you forget the detail of the equation, no problem. You can always come back to these slides and look for it. Or you can go for a textbook that discuss about turbulent velocity in detail. So this one is just an introduction to you guys that we have an equation to define turbulent velocity profile. Okay, so the one in the box here is to the velocity profile that you plot from the experiment, that you get from the experiment. So the one that you can see this experiment, the plot from this graph. So you can see that your U plus equal to 2.5 ln Y plus 5. This is the experiment data that you plot from this experiment. So you see that there's a straight line. So this actually is a straight line. Yeah, you see there's a straight line here. And a technical term to introduce to you today is called viscous sublayer. So viscous sublayer, it means that there's a section inside a pipe, especially very close to the wall. When we know that when you have a fluid that flow in the contact of the wall, then viscous effect will take place. So just take note that there's a term called viscous sublayer. Viscous sublayer means the zone that very near to the wall, where the viscous effect is dominant. And then you see there's a U plus Y plus in the chart. Let's say you have a chart to look at, and the chart gives you U plus Y plus graph. If you see that the Y plus region, this region, if you have a U plus equal to Y plus, yeah, if you have a region where you can plot U plus equal to Y plus, Y equal to X, where you have a straight line here, it means that you have a mean velocity profile over here. Yeah. And in this experiment, or from this graph, this mean velocity profile, or you have a linear relationship up to Y plus value 5 to here. And then there is a name called Laminar layer, where this line you use log, right? Or this line you use log, because this region, you see that there's an equation in the graph, U plus equal to 2.5 ln Y plus 5.0. This is a equation, and this equation are using log equation, so we call it this is a logarithmic layer. So during this layer, the viscous effect we can ignore. Right? During this layer, during this logarithmic layer, viscous effect we can ignore. And then it's valid up to Y plus 30 up to here. Okay. So you can see that I draw with a 2 line here. So between Y plus equal to 5, Y plus 30, you have a region, we call it buffer layer. So from 5 to 30, we have a buffer layer. So this is about the turbulent velocity profile, yeah. And these are the equation for turbulent flow, the velocity profile. When you see U divided, small u divided by U, and there's a 1 minus R, the R ratio, it means that this is the velocity profile. And if you compare side by side, if you see something that 1 divided by N, it is a velocity profile for turbulent flow. Yeah. So the rest you can read from the slides here. The N here developed, again, it is determined through experiment. So the N from Hin's experiment, the N was determined to be, or was calculated, or Hin's was found out that the N equal to minus 1.7 plus 1.8 log a Reynolds number. All right. So this is according to Hin's experiment. So there is a chart for that one, for this for the relationship between the for the velocity profile. And this kind of because if you look at this equation, we have a power something. So this equation we call it power law. We call it power law velocity profile. Okay, and every time when you heard a conversation between experts, when they talk about power law, it means power law with velocity profile means they talk about turbulence region, right? Turbulent region. So most of the time when you come to your final year projects, if you deal with ANSYS simulation or you deal with flow simulation, then most of the time you will be simulating a turbulent flow scenario. And this one is another graph for that one. Yeah? So you can see the differences between laminar and turbulent behavior, as you can see from the graph here. Okay. Okay, so I will stop here. Tomorrow we will continue with head loss calculation. All right, let me stop the recording.
Okay, so.